Morning, everybody. Are we okay? Everybody came in so quiet.
Scary out there.
Scary out there. Well, you're safe in here. Except for the fact that we're starting magnetism and it's no longer going to be safe. This is my second favorite topic in physics. Okay, my favorite one is optics, which we'll get to after this unit, right? But I love this stuff. I like electricity too, but magnetism, oh my gosh, it's so good. It's so good. I mean, come on. Here we go. Right? You can feel them pushing, right? These are a special kind of magnet called a neodymium magnet. It's made out of some kind of rare earth metals. These are strong. Whoops. It's not strong enough. Come on. Oh yeah, they're strong. Right? Okay, and they're strong enough that I can feel like blood flow restricted as it pushes, right, from the vein to the back of my hand. But like, how does that work, right? It's like okay, got it off. Good. These are pretty strong magnets, right? Okay, and magnetism is something that's always just tickled me, right? Because things can happen at a distance, and there's pushes and pulls. It's like really strong, right? I can feel it in my hands. I can get two magnets together. I can magnetize things. I can take paper clips, right? We're going to jump in to all of that. And this is just fantastic. And we're going to explore the ramifications of magnetic fields, what it has to do with all this electricity that we've been learning about. And eventually, by the time we're done here, we are going to be able to explain most of the universe. It is absolutely incredible. I mean, oh my gosh. Okay, where do you start? There's so many things to talk about. Let's talk about what you know already about magnetic fields, either just from living or from reading and studying all that kind of stuff. What's something you know about a magnetic field? Yeah.
They come in pairs of opposite poles.
Okay, so there's poles now, right? So like when we did electricity, there was charge, and you had a positive charge and a negative charge, and they could be separate and different or together or whatever, right? Not so with magnets. Magnets are called dipoles, meaning they always come together with two poles. Okay, we give names to those poles. What are the names? North and South Pole, okay? But a magnet will always be a North and a South Pole. You can take a magnet, that bar magnet right there, and cut it in half, and you will get two magnets, both with North and South Poles. You can cut it again and get North and South Pole. You can keep cutting that magnet down until you get to the atom. And an atom will have a North and South Pole. Magnetism is built in to the structure of the universe. Just like charge is, just like mass is, magnetism is always there. The Earth has a magnetic field, right? And if you get another magnet and you suspend it in a liquid, okay, what can you do? What is this? It's a compass, right? And what do compasses do? They point me way home. They don't point home, well, unless you're Captain Jack Sparrow, in which case they point you to the Black Pearl. Or the Isla de la Muerte. I can't remember where his compass pointed, right? But like, beyond magical compasses, although I would argue that this is magic. Like, you just... right? No matter how much I turn, right? It's always telling me which way north is. Or is it? What do we know about North and South poles? What are the rules? Opposites attract. Okay? So, I've got up here, see if I can put it on the screen. Didn't test to see if this was going to work. Please work. Ah, there we go. Okay. So I've got this magnet on a stand. Okay. It has a north and south pole, which you can't see right now. Okay. And I've got another magnet. Okay. Of the same color, right? So red would be red, green, they'd be the same poles, right? Okay. So if I come in here and I try to, what does the green end always want to do? It's being attracted, right? So the opposite poles attract each other, okay? And if I try to put two poles together, you see how it just ran away, right? In fact, the red end wants to be as close to this green end as possible, right? Okay? And so I try to come in with the green again. It gets chased away. It's like I have the force. The force, not a force. There is a force here. But. Okay, so we know that opposites attract. So that means that the red end and the green end are opposite poles, right? The opposite poles want to line up with each other. But what's going on here? If I kind of put them over the top of each other and I twist, do you see how they line up still? Okay, opposite poles attracting each other, okay. What kind of force causes a twist? Oh no, it's a word that you don't want to say. Torque. And you just thought this day couldn't get any worse. Okay, all right, but there's a bigger mystery here, right? We know that opposite poles attract, right? Keep that in mind, that's the truth. Okay, I'm going to reveal the poles on this magnet, right? So that means north to south and south to north, right? Okay? The North Pole, this is a compass, by the way. You put a magnet and you get it allowed to spin freely, it's a compass, okay? Where does the North Pole of a compass always point? Where does Santa Claus live? Where do penguins live? Which way does the north end of a compass point?
South.
Where does Santa Claus live? You've been lied to your entire life. Because that way, the direction to Santa Claus and Canadians and Alaskans and polar bears is really the Earth's south magnetic pole. How do we know it's the Earth's south magnetic pole? Because the north end of a compass points that way. Why do we call it the North Geographic Pole? Because the north end of a compass is pointed that way. But in order for the north end of a compass to point that way, what does that pole have to be? And penguins and Antarctic researchers and dry valleys of Antarctica, that way? What does that have to be? The Earth's north magnetic pole. So the magnetic poles of the Earth are opposite what we label them. It gets worse. Every 1 million years or so, they flip. North becomes south, south becomes north. The average time is like 750,000 years, okay? It's been more than 1 million since our last flip. We're overdue. So what happens when the poles flip? We all gonna die? No, we have GPS now, right? We don't need magnets to go places, okay? It's actually really cool, the pole flipping. It takes place over a period of about 1,000 years for them to migrate around. They're currently migrating, by the way. The north pole of the Earth, the north geographic pole, the axis of rotation pole, is not located in the same place as the Earth's north magnetic pole. The Earth's north magnetic pole is like in the middle of Saskatchewan somewhere, okay? Offset from that. And we have records going back to the early 1800s of where the north magnetic pole was, and it's been wandering around, okay? The south magnetic pole is doing the same thing. It's actually sitting in the Arctic Ocean, kind of next to the Atlantic Ocean, but they wander around a bit. And then during that period of flip, it takes about 1,000 years, we end up with not north and south, but we end up with quadrupolar fields, where there's 2 norths and 2 souths, even octopolar fields where there's 8. Okay, and then eventually it settles back down into the bipolar configuration that most of our civilization has grown up in. So anyway, and you thought you knew where Santa Claus lived. So what do we know about magnetic fields? Magnetic fields, okay, have these poles, okay? And we label the poles north and south, but again, it's just the label. Thank you. This one's ideally easy to fit. I hit the right button. Yay! Okay, north and south. But again, just the label, they're opposites. And like the rules we had for electricity, opposites attract, likes repel, that's kind of nice and good. But this pair, right, you always have them together. There is no such thing as a magnetic monopole, meaning just a north pole somewhere. There will always be a north and a south pole. It's a dipolar field, and the fields form closed loops. What do I mean by that? When it comes to imagining or thinking about the field lines that make up a magnetic field, there are a couple of rules. First of all, they are closed loops, meaning they're never-ending circles, ovals, circles. Their shape depends a lot on geometry, but they don't really have a beginning and an end. Remember how in electricity we started electric field lines on positive charges, and they terminated or ended on negative charges? Magnetic fields don't do that. But you're going to see the wrong pictures on the internet and wrong pictures in books and things like that, because there is a rule that we say that the field lines come out of north poles and they go in at south poles. Notice, we're not saying they start on north and end on south. We're saying that a field line will have a direction associated, direction of flow, that comes out of the north pole, circles around, and comes back into a south pole. Unfortunately, you'll usually see the pictures drawn like this. Comes out of north, into south, right? And they won't draw the full closed loop of the field. Like, they're not showing you what's going on inside of the magnet. Because inside of the magnet, that loop closes itself. There's no start and end. It's just a circle that goes around. Now, inside the magnet, it's not very circular. It's like a straight line. And again, the field lines can't cross. They can't touch each other. They are an abstraction. We're trying to give you a sense of the vector field of forces that exists around a magnet. But instead of drawing all those vectors, we're going to draw these fields instead, these lines to represent the field. And if lines are close together, what can you tell me about the strength of the magnetic field there? It's strong. And where they're far apart, it's weak. So all of that language of that abstraction, that lie, right, that Michael Faraday came up with, he believed it was the truth, and we found out later it wasn't. But it's such a good idea, such a good abstraction for being able to picture what's going on. We still use it to this day. So if I have a bar magnet right here, right? And this is the north pole of this magnet. What does the field look like around this magnet? I use the word around very carefully, because what does the field do? It comes out of the North Pole, circles back, forms this closed loop, right? And comes back into the magnet, goes back up and goes around, right? But it's doing it in 3 dimensions. And so it's almost like there's this fountain of field lines that's coming out of the top of this thing, right? It comes up and it goes all the way, and then it circles back around and comes back in to the bottom. This gets further confused by pictures that you will see. It's not that they're wrong, it's just that, well, they're cheating a little bit, okay? You might see a picture where a north and a south pole come together. And again, they won't draw, and I'll do this eventually, they won't draw the full field. They'll just draw field lines going from north to south. Those are magnetic field lines. For all the world, it looks like an electric field, right? Like it's starting on north and ending on south. We're just not drawing the whole, like we're not drawing this end of the magnet, this end of the magnet, and them going around and right, and then confusing the drawing, right? Oftentimes we will sort of zoom in, okay, at a location in space where the field is, and just analyze it there. So you will see again, picture this would be the north end of a magnet, and then field lines are coming out of this north end of the magnet, and they're just drawing them like this. Well, why did they end? Where are those field lines going? To infinity, or looping back around outside of the context of our drawing, right? But I do want to hammer home that unlike, it's very distinct. This is not just another form of electricity. Magnetism is unique in the sense that you cannot have just a north or a south pole all by itself. They're always dipoles, they are always together, and the fields always eventually close on themselves. Unique from electricity, where fields can begin and end, have a start and a stop. And you can have a positive charge all by itself, or a negative charge all by itself. It's part of what makes the magic and makes it different. Although we will talk about it tangentially, or we'll sort of skim the surface of it, it's really not a field of forces, per se. Obviously magnets exert forces on each other here, okay, right? You can't see it on the screen, but I'm spinning this thing over here, right? Just by wiggling a magnet around it. It's really torque, okay? So it's almost like a torque field. If that hurt your brain, I don't blame you, because it definitely hurts mine. But luckily, we're not gonna have to go too deep into that. All right. Let's do this quiz. I may not have prepared you sufficiently for it, but we'll see. But now we have to talk about forces. Okay? And this is where it really starts to go off the rails. I'm going to drop the equation on you first. And then we're going to talk about implications and visualizations and a whole bunch of stuff. Okay? So we are going to leave permanent magnets behind for now. We're going to get back to what makes a permanent magnet a permanent magnet later, because the answer is a little bit complicated. But I want to talk, so to be able to express a field, we need to be able to talk about force. We need to be able to talk about a vector thing, okay? And so the force, it's called the Lorentz force, by the way, just because Lorentz wrote it down first. The force that this is going to sound weird, the force that a charge experiences in a magnetic field is equal to the magnitude of the charge, not its sign, just its magnitude. Your book will write absolute value signs on it or something. okay, times how fast the charge is going. Notice this is also a magnitude. Times the strength of the magnetic field. And this is the first time you're seeing this symbol for the magnetic field unless you've been doing your reading. Okay? We use B for magnetic field. It's because capital M was already taken for something called magnetic moment. Times the sine of the angle between the velocity and magnetic field vectors. This is a magnitude equation. And it doesn't give you anything about direction. But let's unpack some things here. Let's not worry about the sine theta for a second. Okay? First of all, charges experience forces from magnetic fields. But only if they're doing what? What does that charge have to be doing? It's got to be moving, right? It has to have velocity. If the velocity of that charge is 0, how much force is it going to experience? None, right? And of course, if it's neutral, it's not going to experience anything either. And that's a dead giveaway, by the way. If you've got a particle and you fire it through a magnetic field and it does not deflect, what do you know about the charge on that particle? It is 0. It's neutral, right? Magnetic field. I mean, unfortunately, we can solve for the magnetic field, right? It's going to be the force divided by Q, V, sine theta. And again, I'll get to sine theta in a second. What are the units of this thing? What are the units of force? Newton, charge, coulombs, velocity, meters per second, sine theta. No units. What the heck is a Newton divided by a coulomb meter per second? Answer? It's a Tesla. Not the car. The car was named after the guy, and we named the unit after the guy. Nikolai Tesla. We'll talk a little bit more about him later. Okay? But the SI unit is Tesla. The other one that you might hear when it comes to magnetic fields is the Gauss. Yes, that Gauss. Gauss's law Gauss. Okay? 1 Tesla is 10,000 Gauss. Gauss is 10, it's not the SI unit, but it's a close cousin to the SI unit. It's just, we're just arguing over a factor of 10 here. The reason Gauss comes up is because the Earth's magnetic field is often expressed in Gauss instead of Tesla. It's just what the geologists do, and kind of like chemists always using centimeters and grams, and the physicists are yelling at them to use meters and kilograms, and they're like, no, it's basically the same thing. But yeah, we'll use Tesla always in here for the strength of magnetic field. And again, please just like, don't try with the unit. Just, if you've got a force, put it in newtons. If you've got a speed, make sure it's in meters per second. If the get the charge and cool. If you do all those things, you're guaranteed to have a Tesla come out, right? Because the equations know how to handle all of the units. The Earth's magnetic field is about half a Gauss. It does vary in its strength from place to place. And half a Gauss would be, what is that? 0.5 times 10 to the negative 4 Tesla, right? So yeah, 5 times 10 to the minus 5 Tesla. So the Earth's magnetic field in Teslas is really small, which is why I think geologists like to run around and talk about Gauss, right? Because they can just say half a Gauss instead of 1/10,000th of the Tesla. By contrast, these magnets I showed you earlier, okay? These are about half Tesla magnets. Okay? So these magnets right here are about 10,000 times stronger than the Earth's magnetic field. You saw that, the neodymium magnets I had on the Elmo also. You saw how I brought that magnet in and got the compass to twist around and stuff, right? I overwhelm the Earth's magnetic field, right? That compass could care less where Santa Claus lived, as long as that other magnet was nearby, right? Because the magnets I had were way stronger than the Earth's magnetic field. That Earth's magnetic field is pretty weak, but very, very important. Because the Earth's magnetic field is able to apply forces on charged particles. And what's our biggest source of charged particles? Well, they are electrons and actually free protons coming from somewhere. It's hidden today because it's raining. The sun. What is the sun? It's a big nuclear bomb. It's going off all the time. Big thermonuclear bomb. Okay? And it provides us warmies, energy, food for plants, and all kinds of stuff, right? Okay? But the energy that comes from the sun isn't just in the form of electromagnetic radiation or light. It's also putting out a whole lot of charged particles. Really energetic ones. The kinds that can cause cancer and do a whole bunch of bad things to us. I'm not talking about UV rays. UV rays are light. I'm talking about actual electrons, protons, other things, helium nuclei that are just being blown off the surface of the sun. It's called the solar wind. It moves through our solar system. And it comes careening into Earth, where we have a shield. What's our shield? The magnetic field. The magnetic field shields us because the Earth's magnetic field is able to apply forces to those particles streaming from the sun and cause them to deflect. In fact, the particles begin to circulate around the magnetic field lines of the Earth and then will, with all of their energy, come colliding into the Earth's atmosphere, causing something called the aurora borealis, the northern lights. Northern lights, which you can't see at our latitude here on planet Earth, you have to go much further north into Canada and Iceland and all those places. And they also happen, the aurora australis happens in the southern hemisphere. Those lights in the sky, the curtains of lights in the sky, are caused by charged particles from the sun slamming into the Earth's atmosphere, riding the Earth's magnetic field lines to their sources. In the North Pole, which is really the Earth's south magnetic pole, which way is the magnetic field pointing? In or out? In, right? Okay, so the magnetic field lines are going into Canada, they're coming out in the southern Atlantic Ocean. Positive and negative charges go in different directions. It's kind of fun. Anyway, so those forces are real, and next week's lab I'm going to give you some demonstrations. I can't do them in here, but I'll give you some demonstrations of charged particles being deflected by magnetic fields in lab as we explore some magnetic fields. So force is governed by charge, how fast they're going, and the strength of the field. But what does this sine theta have to do with anything? And Mr. Balogh, I have a question I don't want to ask, but I'm going to ask it for you anyway. That's the magnitude. What direction does that force point? Because it's important to know the direction of force, isn't it? Because when we go to add them together, do anything else with them, it's a thing. Okay. How you doing so far? How's this information hitting you? Kind of okay? I mean, some of it's new. Some of you are going to go home and write a really nasty text to your parents about Santa Claus. But, you know, you're okay, right? Okay, this is where you're not going to be okay. So this is where it goes directly off the rails. Three things. Velocity is a vector, it has a direction. The magnetic field is a vector, it has a direction. And this force has a direction. Those three things are always perpendicular to each other. That means that if I have a velocity, let's say the velocity is pointed up, and I have a magnetic field, I don't know, let's say that it's pointed to the right, okay? The force that this charge moving at speed v feels has to be perpendicular to the velocity and the magnetic field at the same time. There's only two directions where that can be true. What directions are those? Question, comment? Yeah, we're going three-dimensional. What are all the directions that are perpendicular to V? Just look at V. V's pointed up, so what are the perpendicular directions to V? Horizontal and in or out. And every combination of horizontal in and or out there can be, right? Okay, now look at B. What are all the directions that can be perpendicular to B? Up and down, and in or out. What direction was the same for both of those? In or out. Right? They shared a mutually perpendicular direction, which is in or out. That means that this force that this charge feels is either into or out of the screen, which is a two-dimensional surface. And now we're talking about 3 dimensions. We must live in 3 dimensions. Okay? So we have a situation here. I gotta get my colors right there. B was green. Velocity, here we go, velocity. Boy, this is good Velcro. Velocity, B, okay, right? So we have velocity pointing up, and we have magnetic field pointing to the right. I don't know if you all can see that from back here, right? But I tried to get the colors to be the same, right? What direction is the force pointing? It's pointing out. Say that loud.
How do I draw?
How do I draw that? What is going on? Why is my life got so fast? We'll get to how you draw that in a second. Okay, let's just investigate the ramifications of what's going on here, right? Because up until this point in your physics career, and I am including physics 2A in this statement, we have avoided the 3rd dimension, haven't we? We was like, oh, well, you could do the Z, but we're not going to do it. Now we're doing it. Okay? So, how do you know if it's out or in? Right? Because both of those directions could be mutually perpendicular. How do I know which one it is? The answer is the right-hand rule. Everybody raise your right hand. Okay, I'm just making sure. Okay? You can put them down now. I'm just making sure you all know which one's your right hand, because I guarantee you sometime in the next 3 weeks you are going to forget. I promise you. This is what's going to happen, right-handers. You're going to be sitting there doing your homework. You're going to be sitting there doing the exam. All straight. Right? And you're going to have to do a right-hand rule, and guess what you're going to do? Right-handers, you have to put your writing instrument down. Do the right-hand rule, pick it back up again and go. If you were one of the blessed left-handers, we love you left-handers. 10% of society, you're okay, right? You can do the right-hand rule and write at the same time, okay? It's just you gotta do whatever funky way you need to write in order to not smear the page, right? Okay, so get a Post-it note. Get a tattoo, do something, okay? Label this hand. One of the preeminent philosophers of our age, Winnie the Pooh, said, I have no trouble telling my right paw from my left. It's knowing which one to start with that makes all the difference. It's deep. That's deep. Okay? You take your right hand out, and there's lots of different ways to do this. This is not my favorite, but I think it's the one that works well for most students, okay? You take your hand and you pew pew, right? Okay, right? But do you see how my thumb, my index finger, and my middle finger are all doing this? Right here, right? Okay? Your finger, okay, is the V. Your pointer is the V, okay? Your middle finger is the magnetic field, and your thumb ends up being the force. Again, get a tattoo, label them with Sharpie, we'll do something, okay? But the fingers V, middle fingers B, thumb is the force, okay? You take your hand, you line it up with the two vectors you have. My V goes up, my magnetic field goes that way, and my thumb is pointing which way? In. See how my thumb points into the screen? Let's see if we get this right here. Did I screw something up? I did. Oh, this thing is not colored correctly. I can't go with colors. Sorry, I should have gone with correct colors on the screen. I invented a left-handed coordinate system as well. Velocity, field, force. There we go. Okay. I was doing the left-handed rule inadvertently. Okay. So if I do my velocity up and I do my magnetic field, you'd think I'd know how to use this thing by now, right? Okay. Force. There we go. Okay. My velocity is up. My magnetic field is that way. What direction is my force pointing? Into the screen, right? Finger be up, be that way, thumb goes into the screen. Let's reverse. I'm going to change my colors now, just to be confusing. There's my field. No, that was my force. Which one's my field? My field was green. And my velocity was blue. Okay, here I'll go over and fix this one real quick. Okay, there's my velocity. Okay, so now we're doing the second. Oh, so we said the force was in, right? Again, we'll get to how you draw this in a second. Okay, so now if I've got this one, my velocity is up. My field is to the left, and which way is my force pointing? Out of the screen, right? So how do you do that with your hand, right? You need to make this thing your hand, right? So, again, pew pew, right? V points up. So you just point up first, right? Then use this magnificent wrist that evolution has given you, right? To rotate so that your magnetic field, your middle finger points in the direction of the magnetic field. Your thumb gives you the direction of the force. Which way is the force pointing? Out. This is called the right hand rule. And you are going to look amazing as you do your homework. Because you're going to be sitting there doing your homework and, right? Go to the library, down, grasp. You can identify the physics 2B and 4B students. Because they're sitting there doing this. There's a magazine called Physics Teacher Magazine. You can imagine how exciting it is, right? On the back cover of one of the issues, they had put a picture of a bunch of students and they said, guess where these students are from? It was a classroom, they were obviously taking an exam because you could see the stress, right? But they were all of them in some right-hand rule configuration, right? And the whole point of the thing is that you really can't tell where people are from because the right-hand rule is universal. My uncle, who's a geologist, was in Japan giving a lecture, and he was trying to talk about Earth's magnetic field. He was talking through a translator, right? And he could tell that the audience wasn't, like the translator was either messing up or the audience wasn't getting what he was saying. And he just turned to the translator, he said, wait a second, I've got something, okay? He said, just stop. And he turned to the audience and he did this, which is another version of the right-hand rule we're gonna learn, right? 110 people in the room, Japanese scientists, all geologists, went, oh, yeah, right? Right? Because it's like physics game science. Okay? It is internationally known, it's part of the physics mafia, right? That right-hand rule. Okay, so there's variants of this where we can do things like, this is the force. This is the direction the velocity is going. What direction is the field? So what do you have to do? Besides dislocate your shoulder, you have to turn around, right? Okay, right? Okay, number one, if you are doing the right-hand rule and you are causing yourself physical pain, the mental, emotional trauma is fine, but the physical pain, you're doing it wrong, okay? Right? There should be no bending of fingers back. Right? Okay? What do I put? So first of all, I know I can put my finger down, right? Velocity down, but now what do? I've got to rotate my wrist so that my thumb points in the direction of the force, right? And then what direction is the field? Going into the screen. I'll do it with this thing here, right? The force is over there, force that way, velocity has to be down. So which way is the field pointing? Into the screen. There's a lot of people in here training to be physical therapists, your hand will be okay. Okay. Mama, do you want to ask your question again?
How do I draw?
How do I draw this? So there's actually, again, an international standard for how we draw these things, okay? In 3 dimensions on a 2-dimensional surface. Drawing in 3D sucks. Like it just does, okay? Most people aren't good at it and you have to train for a while, all that kind of stuff, okay? To get perspective and all that, whatever, okay? So physicists, we don't do it, okay? What we do instead is we introduce the 3rd dimension by talking about what direction the vectors are going. So in this first example, B was up, B was to the right, my thumb has to point into to get the force. I would draw that force as an X. And over here in the middle, V is up, V is to the left, my thumb's pointing out of the screen. I would draw my force as a dot. X means into the screen. Dot means out of the screen. Sometimes you'll see it where they'll do it in a textbook, they'll draw a dot and then they'll put a circle around it. I don't do that. I just put, there, that's all going out of the screen. Okay, right? And it can get a little bit messy after a while. Okay, if you see this, if I say the magnetic field is like this, what do you now know? It's pointing into the screen. What are all of the X's? What are all of the dots? What is a vector? It's an arrow. And if that arrow is pointed at you, what do you see? The tip. And if an arrow is moving away from you, what do you see? The feathers. Right? okay, like shooting an arrow, right? You would see the feather end moving away from you. That X are the feathers, the end of the arrow, okay? The dots are the arrow tips. So you're like, well, Mr. Balogh, I hunt, I tips them, okay? Too bad, too crap. So how do I draw the magnetic field in my third picture? Right hand rule is telling me force, velocity, my middle finger's pointed into the screen. So how would I indicate the magnetic field for this one? I would put an X and I'd label it like that. So if I have a magnetic field in a region of space that looks like that, and the particle experiences a force in that direction, what direction is the velocity? What do you have to do? You have to get which hand out? Your right hand, okay? And what do you know? Okay, I know that the force is this way, right? Okay, and I've got to get my field though. My middle finger needs to be pointed which way? Out. Don't do this. Do this. Right, okay. So my force, that way, field out. Which way is my velocity pointing? Down. We draw in 2 dimensions, but we live in 3. Everything I've told you is true for positive charges. I'm going to give you more fuel for hating on Ben Franklin now. Because for negative charges, what happens? It's opposite. And by opposite, what I mean is this. You will use the right hand rule. You will figure everything out, and then you will flip the direction that you find. The opposite comes at the end. You know this piece of information. I'm going to shock some of you, but for others, you're going to nod your head. There are lies on the internet. Okay? Not everything's true on the internet. And one of the biggest lies that is out there is this thing called the left-hand rule. You will see it. They'll say, well, if there's negative charges, use your left hand, it works. The left-hand rule is not allowed in my class. Okay? Not because I have anything against left-handed people, right? What I've noticed is that there is more confusion and learning is stunted when students use the left-hand rule. If instead you just stick with the right-hand rule and flip for if it's an electron, do everything and then just flip the direction of your force field, whatever it is at the end, students tend to do better. I'm not saying that's you individually. If you want to do the left-hand rule, you're more than welcome to do the left-hand rule. I will not help you because I can't do it. It's confusing. I've noticed students will screw up a lot more. They'll start using the left hand for positive charges and vice versa. If you standardize on the right hand rule and just remember that Ben Franklin's an idiot, you gotta turn your hand over. There's much less room for error. It's equivalent to just having to remember a minus sign when things go down, right? You just gotta start thinking, oh, negative charge, I'll do it backwards. Christian, oh, sorry. Great.
For the up thing, why isn't it like this?
For this thing?
Yep.
So the force was this way, right? Okay, and now I need to get my middle finger to point out. But if I rotate like this, now my thumb's not pointing the right way. The only rotation I can do is this way.
Wait, the thumb is the force, right?
Yeah.
Oh, okay, never mind, I get it.
It takes a while. It does. You're gonna screw up. And I'm not gonna try, but I would just love to see what you guys are gonna do in the Discord.
For negative ones, do you flip all of the forces?
No, you do the right hand rule as usual, and then
Just flip whichever
you
one.
flip the direction. Right? If this were an electron instead of a proton, or say positive charge, right? I would do everything. Ignore the V because we don't know it yet, right? My force is this way. My field's this way. I'm learning that the velocity is down. Oh, negative charge? No, it was moving up.
Okay.
That's what you do. You get to your answer as if it were a positive charge, because there's consistency in applying that right hand rule over and over again, right? And then, oh, negative charge, I just flip my answer 180 degrees. What happened? Not seen that before. There is no setting for make this video play real fast. We will reopen that file. Which chapter we have? 21, right? Now it's playing the right speed. What's going on? So beam of electrons, and they've made it so that you can see the beam of electrons, right? Don't worry about the thing in the back. It has nothing to do with this. Okay. Oops. So beam of electrons, and they'll bring in a magnet. Bring in your magnet. Okay. And do you see how the beam of electrons is pushed, deflected? Which way is the force? It's down, right? They're being deflected down. Now they're going to reverse the magnet. And do you see how it's deflected upwards? I wanted you to see, right, that these charges get deflected. We can actually apply the right-hand rule to this and figure out what direction, the magnetic field's pointing and all that kind of stuff. But let's move on and talk a little bit about where you might have run into this. And you're like, I've never seen anything like this in my entire life, Mr. Balogh. Okay? Actually, you've been very near one. This is called cyclotron. Okay? It's a rudimentary or early form of a particle accelerator. And it turns out you can use magnetic fields to cause particles to speed up, right? We are applying a force to a particle. If we can apply that force a certain way, we can get it to speed up. So what does this do? Okay, so we've got two big magnets, and you can see in that top picture up there, there's a gap, right, in between there. In the gap is where the particle is going to speed up. But in the magnetic field is where this particle is going to turn. Why would a particle turn? What direction is the force for a particle that's moving at speed v in a magnetic field? The direction of the force is always which way? Perpendicular to the velocity, right? So as a particle enters a field, is it going to continue in a straight line if it's experiencing a force? No. What's it going to do? It's going to deflect, isn't it? It's going to deflect in the direction of the force. Well, now it's over here. What direction is the force? Over here. What direction is the force? What direction is the force no matter which way this particle is moving in a magnetic field? Towards the center. What will a charged particle do in a magnetic field? It'll circulate. Because that force is always perpendicular, always pointing towards the center of the rotation, we now have a centripetal force. And what is the path for objects that experience centripetal forces? So you put these particles in these strong magnetic fields where they will circulate. But if they're just circulating, okay, they're not speeding up or slowing down, they're just maintaining their speed. But if instead you give a gap, and inside that gap you put an electric field, is that charge going to experience a force from the electric field? Yeah. So give it a push so that it goes faster. And then it arcs around and gets to the gap again and gets another push and goes faster. What will happen as you speed up, the radius of the circle will get bigger and bigger and bigger. So you can put a charge in at the center moving very slow and speed it up so that it comes out really fast at the edge. Why would you want to do this? What is the point? Why would you want to accelerate particles to very, very high speeds? The picture on the right is a picture of the very first large-scale particle collider that was ever built at Lawrence Berkeley National Labs. Okay? It took up a building. Those are people, right, in that picture right there. It's huge, right? And they sped up electrons to very close to the speed of light and then banged them into other electrons. Why? Because physicists just don't grow up. We just take our toys and go smash them together. No. We wanted to find out what they were made of. How do you find out what stuff's made of? Smash it. Right? But this gets a whole lot more personal very quickly. Anyone that's ever had a medical diagnostic done where you had to have, say, a radioactive tracer injected either into your bloodstream or your GI tract or your brain so they could take pictures of what's going on inside your body without having to cut you open and let the demons out? Where do they get their radioactive samples? Is it the nuclear bombs? No. They get them from the basement. The basement of the hospital, usually a larger hospital, okay? But there's several in Fresno, okay, that can do this. Because the half-lives of those radioactive isotopes that are being used in medical diagnostics are measured in minutes, meaning that when you make it, you have about 30 minutes to get it into a patient and take a picture before it's going to be gone. You can't make this stuff in New Jersey and ship it to California. You have to make it in the hospital or very close to the lab where you are getting the diagnostic done. And how do they make radioactive isotopes? Take some electrons, make them really, really fast, and slam them into things. And they become radioactive. Particle accelerators are saving lives every day. Let's do a quiz and see how you are doing. All right, couple things of business before I let you go. First, homework for this chapter is not due this Saturday, right? It's due next Saturday. There is only one grasp between now and then. This Friday. Because next Friday is what? A holiday. Yes. This school takes Friday and Monday off. We have a 4-day weekend. Okay? For the President's Day holiday. Okay? So you need to make sure that you are planning. Because this grasp is kind of it. Because there's no grasp next Friday, right? Second of all, if you're struggling and having trouble with the 3D nature of what's going on here, I've got a very poor example that I put together And I put a link. I'm gonna try and fix this later today or tomorrow. But I put a link in Canvas for you. Where is it? Go to modules. If you come down here to Unit 2, there's a new link under the Chapter 21 resources. It's called 3D XYZ axes. Okay? If you have any browser should be able to support this, and you can do it on your phone. Okay? I'm going to get it better so that the viewpoint is centered on the origin, because right now it's really hard to kind of get this thing to go, like, it's kind of hard to like manipulate it in space. If you have a cell phone that supports augmented reality, this will drop this thing in space right in front of you and you can walk around it. Okay? So give it a shot. See if it works, right? See if it helps you visualize what's going on. But this is just an easy 3D web kit, augmented reality thing that I threw together. I will see you on Thursday.